All right, well, let's get started. So this is, welcome everyone to, what are we at, day 3 of the Maple Conference. This is the algorithms and software track, and we have 4 talks today. So 4 talks and 3 speakers. So the first talk is a contribution by Amir, Hosein, Sadeghimanesh, and Matthew England from Coventry University. The title of the talk is Using Cylindrical Algebraic Decomposition with Equational Constraints to Study Population Dynamics. And yeah, I'll turn it over to Amir Hosein to speak about his work.
Okay. Thanks for the introduction. I hope that everyone is seeing my slide. So my name is Amir Hosein Sadeghimanesh. I'm working in Matthew England's group at Coventry University, and our work is supported by DualCAD project. I will go very short presentation of what is the summary of this work. If you want the longer one, the video is available on my website. So previous year, I joined the Gergely Roche group in Hungary, and we started studying population models. Just to have a very quick recap, what is a population dynamic? You have some species, they can be humans, animals, bacteria, depending on the context. And let's denote the size of that population of that species with capital N. Then N dot means derivative of that variable with respect to time. The simplest model that you can find, and maybe you have seen in your calculus courses, is logistic growth. What happens is that the population start growing very fast at the beginning, but they cannot grow to infinity because of the limitation on the food, resources, space, and everything. So there is a maximum capacity, they can grow up to that. When they start getting close to that, the speed of growth will be reduced until they become like near to a stable thing. And a stable means like the population doesn't change anymore. So you have 2 steady state, the extinction, if you start with 0, remains 0. And if you start with non-zero population, then you grow up to reaching the carrying capacity. A more fun model is a strong alley effect. Here, it's not only competition for the resources, but you also have cooperativity. Let's say the species are helping each other for survival. Therefore, you need to have more than some number of these species for the survival, you reach the carrying capacity. But if you have below that threshold amount of that thing at the beginning, then they will start dying out. There are plenty of examples of them. Some starfishes show this behavior, some trees or some insects, etc. And then a more fun question is when you have several of these populations, let's say in different geographical environment, or it's a different wells in your experimental lab, in the experimental plate in the lab where you are studying bacteria, and then you spare them to each other, etc. So you have several places with some species showing this behavior, and you connect these places in some way, and there is a rate that they can go to from one patch to another patch. And then you want to know how many steady states they have. So this was studied before for small value of dispersal rate. When the strength of connectivity is very small, they behave like several disjoint models. So you get 3 to the power n steady states. If the strength of connectivity is high enough, then you can think it is like one big well-mixed model, and they will have 3 steady states. What was thought before was that when you decrease the strength of connectivity from 0 to a very large number, the number of steady states monotonically decreased from 3 to the power n to 3. That was something that was thought before. So previous year, we tried to check if this really is true or not mathematically. So we use some algebraic tools. Just to make it short, you can watch the whole video later. you have some polynomial equations involving both variables and parameters, and then you want to know like for which value of these parameters you have how many solutions. The first step is to get rid of the variables and have some polynomials only with parameters using Grobner basis and elimination. Many of you may know about these things. It gives you the boundary between regions where the number of solutions can change. And then the second step, decompose the parameter space with respect to these boundaries so that you have finally many connected open sets, and then you need to check only one point from each of these regions, and then you can get the final answer, let's say, where you have how many things. So this method is implemented in Maple already in a package called root finding parametric. We started for 2 populations. The computer did finish the computation. We got, well, the conjecture looks true. For n equal to 3, unfortunately, the memory got full. The computer stuck. We couldn't see the final result. Then we thought of mixing this deterministic tool, algebraic tool, with numeric thing. So what we said at fixed value of one of the parameters and let only one be free. So what you get now is intersection of the boundaries with horizontal lines. There are some points. The second step is to find where the number of these intersections change. You got this, and the final result for the 3 patch was this shape, which in a tiny region here we zoomed, and we see that the number of SSS can temporarily increase, and the conjecture was not true. But this year we thought in QFNRAY that let's see what is wrong in the, where things go wrong and memory gets full in the deterministic tool with all parameters free. The first step, which was using Grobner basis, was already like making the memory full. So we thought of replacing this step. An alternative is using the projection step of the algorithm. It produces the boundaries and some more curves. And it's still doubly exponential, but with the help of equational constraints, you can reduce the complexity a bit. And up to when I was recording and making these slides, we were at this stage, but when we were writing the proofs, we found that we can even go further and make it even shorter than just using the equation constraints with less boundary curves and more exact the boundaries. But anyway, so this picture is for before we find that we can optimize it even more. Now with the optimized one, we don't get this this curve here, so it will be better anyway. So we did the computation and we figured out that, well, the numeric result of previous year is completely exact. The good things is that you don't need to use Grobner basis, you don't have numeric computation, but being free of Grobner basis, you should be careful that we still use computation sum resultants, which is determinant of some matrices. If they become big, then being free of Grobner basis is not that much advantage. But at least at this example that the previous method with Grobner basis was failing, this new method is not failing, and we could see the things deterministically. So I will stop here for this one.
All right, thank you, Amir Hosein. Are there any questions from the panelists? So I'm getting the Q&A window. All right.
I have a question, if I may.
Yeah, go ahead, Jürgen.
So often in these CADs that come from real-world applications, you get a lot of spurious cells, or in particular, spurious curves that make some sense mathematically, but are not relevant for the application. Is there any way you can filter those out or suppress them so they won't show up to begin with?
Some of them, yes. So for example, we got some curves that have solutions only in the negative orthant, or at least it's not in the positive orthant of the parameter space, whereas in this biological context, parameters can only attain like 0 or positive value. But detecting that those polynomials have solutions on not in the positive orthant, some of them are easy. Let's say you only see positive coefficients or something like that, but I'm not sure if there are like more, like can exclude more things. But there are things that one can do.
All right, I have a question from the chat that asks if the equations from the model where the Grosvenor basis failed, if those are available somewhere.
So yes, so the equations for this model are available in the second reference here, which is now published in International Journal of Bifurcation and Chaos. I think 2 weeks ago or 1 week ago got published, so you can look at that. But the bioarchive version also is there. Yeah. So the equations are the three steady state equation for the three patches plus determinant of the Jacobian of these three, because you want to see where the two real solution meet and become complex and things like that. So there are 4 polynomials, but you can find them.
Thank you. All right. So thank you very much for that talk. So I guess we'll move on to the next talk, which is also by Amir, Hosein, Sadeghimanesh, and it's joint work with Matthew England. And this one is on implementation of cylindrical algebraic decomposition in Maple. So I'll give it over to you again.
Okay, thank you. So maybe I introduced myself in the previous one as well, but if you are coming from new, I'm Amir Sadeghimanesh. I'm working in group of Matthew England at Coventry University. Our work is supported by DualCAD. So in previous talk, you saw an application in biology. Now we are doing something in, let's say, satisfiability and quantification things. So you can watch the whole video for the whole story, but here I go like just a very short piece of what's happening. So let's say you have n variables, x1 until xn, and you have some polynomial relations. By polynomial relations, I mean you have polynomial involving these n variables, and also like some relation with 0, like equal to 0 or not equal to 0, smaller than 0, or so on. And you have a conjunction of these polynomial relations. And now the question is there any choice of values for these n variables such that this conjunction of these relations be satisfied or hold? That is called consistency. We focus on this. There are other things that you can answer if you can answer this one with something. So let's just, because we are going to give a short presentation. So let's stick ourselves on very small example. 2 polynomial inequalities in 2 variables, so x and y, and this and this. So if you have, let's say, 2 or 3 variable, then you can plot things in 2D or 3D. And of course, if also the equations are simple enough to get plots. And then the question can be answered by taking intersection of the places that the inequalities, each one is solved. So here is above this parabola. But of course, it cannot be answered this way by plotting things. If you have more than 2, 3 parameters, let's say you have 100 of variables, and or your polynomial is something very complicated and the plot is not possible to in few seconds, minutes, whatever. Then you need to use some more advanced algorithms. Fortunately, there is an algorithm. You can use CAD that is made by clients, whatever it is. The summary is that it receives the polynomials of your inequalities, equations, etc., and it returns you a finite number of points that for checking satisfiability of your initial conjunction of polynomial relations, you only need to check these finite things so you can do it algorithmically. So Rn is simplified to finite set. Okay? Now, on that example, which I had a parabola and a circle, that CAD produced 23 regions and 1 point from each of them. And then you have to check all these 23. So you have a computation to produce these 23, and then checking these 23. If one of them was satisfying the relations, then you say that, okay, the equation is satisfiable. And if none of them satisfy it, then it means it is unsatisfiable. There is no choice of point that makes those two inequations inequality satisfied. Anyway. So that is also implemented in Maple for, let's say, computing the whole CAD. It's in regular chains. It has a different type of outputs, 3 types, and I use the code tools usage to see how much resources they use. So you can see at least it uses 6.1 megabit, and it takes like 62 milliseconds on my laptop. Now, there are other alternatives. You don't need to compute all of those sample points and check them to get the answer. So another alternative is using an LSAT, invented by Jovanovic and Demura. You can see the reference. So the idea is, instead of computing those finite points and then starting checking the things, is you pick up one point, whatever point that you like, you check them. If the question was satisfiable, then finish. If not, then create the biggest connected cell around this point with respect to the relations that it was not satisfying them, and call it a bad region. And then choose a point outside of this bad region. If it was satisfying, stop. Otherwise, create another bad region and choose a new point outside of the union of bad regions, and continue like this until you get satisfiability, or you cover the whole parameter space with these bad regions, which means there is no point that satisfies it. So this is not implemented in Maple. We started implementing it. There is a simple version of it implemented by us in a package called DualCAD, which is not publicly available right now because we still need to do some optimization and we want to add other things. And you can also get info level to see what is happening step by step. So what is happening visually here? So it's first try the point 0, 0. With respect to that circle, it was okay, but with respect to the parabola, it was not satisfying it. And it compute the cell, the biggest cell with respect to only the polynomial related to the parabola. And it gets a very big region excluded at the beginning. And then it pick up a point outside of that. It's still on the curve of the parabola. It's not a good one. It recognizes this one as the second bad region. Now it pick up a point outside of the union of these two bad regions. Luckily, it's a good point, and it's satisfied. So it says the details what is happening, and it says it is satisfied. 0 and 3 is 1 point doing this. Now comparing the amount of resources that it used from memory, 4.4 megabit less, and CPU time 31 milliseconds, which is also less. Okay. Now, it is not the only alternative. There are other alternatives. One of them is called incremental CAD. What this incremental means, watch the more lengthy video. But to be short, let's explain it on this simple example. So it does the projection step of CAD, whatever it is. So it's not still saving from that step, the simple version that we implemented. But in the lifting step, it is saving. So it's not going to compute all those 23 places. So start with the partial assignment at the beginning, assigning nothing to X and Y. Then it pick up one polynomial in the projections for the variable X, and it isolate its root, it's 1, and then pick up 1 point before, 1 point after. So we've got 3 partial assignment. We do 1 partial assignment at a time. So I choose this one. And I put X equal to 2. The 2 inequalities that we had at the beginning are not satisfied. And in fact, we cannot check yet because they still have Y. So we still continue. Now we pick up one polynomial from projection, but from the step that has the variables X and Y, we substitute X to 2. Then it has one root, 5. We pick up 1 point before and after. So it has 3 assignments here. And we pick up one of them, 2 and 6. We put them into the initial relations, it's satisfied, then we stop. So the first full dimensional point that it checked, it's satisfied, or you can consider also the partial assignment, the third check that it did, it hit satisfiability. Now, and also it has the details of what is happening. So the amount of resources that it used, the memory 4.6 megabit, it's still less than the whole project, the whole CAD. And the CPU time 47 milliseconds is still less than the whole, doing the whole CAD. Are they always like using less memory and less time? Well, here we were lucky, but at least we can say that it will not be worse than doing the whole CAD. And these are not the only alternatives that exist. There is non-uniform cylindrical algebraic decomposition, cylindrical decomposition, cylindrical algebraic covering. We are going to implement these algorithms to optimize things, and then yeah, there are some future works. Then we will maybe make it public anyway. And these are the references.
All right, thank you, Amir. So we're open to any questions. I don't see anything in the chat yet. So I found it interesting that the simple incremental CAD, that it seems like it's doing a lot less work than computing the full CAD. Mm-hmm. But it's only about half the running time. Do you have a feeling if that's just because this example is so simple that the full CAD is just very fast on it, or is it just that that your implementation is not, is not optimized yet? Yeah, well, Jürgen points out that
it is not optimized yet, so it's just a simple thing. So I'm implementing things, and then the next step I optimize things. But there are several things. So first of all, this is a simple incremental, so it is like saving things in the lifting. There is also a better incremental, which is also saving things in the projection. So you don't need to have all the projection steps computed before starting the lifting. It computes some part of the projection and start lifting, and then if it's needed, it continues. So there are plenty of things to do to make it even more optimized. And well, of course, you need to be also very lucky if your example is made somehow that the satisfiability region is very tiny and it's somewhere that will be hit very late, then you will get time similar to computing the whole thing. But if you are lucky, like here, the first full dimensional point that you hit, yeah, so there are several things to consider.
Okay, are there any other questions? All right, well, thank you very much, Amir, Hosein. I enjoyed both these talks. The full videos are available in the theater, I believe, and I recommend both of them. Our next speaker is Tereso del Rio, also from Coventry University, also working with Matthew England. And he will speak on comparing the number of real roots of randomly generated polynomials compared to real world polynomials. All right.
Hello, everyone. I hope you can see my screen. Well, as just said, I am Tereso del Rio, and I am a PhD student of Matthew England at Coventry University. And today I'm going to talk about comparing the number of real roots in real-world polynomials and randomly generated polynomials. That was the initial idea, but as you will see, it changed slightly during this last month. So what was our motivation? There is a growing interest in using machine learning for symbolic computation, but these kind of models require huge amounts of data, and the real-world objects we have are limited. There are some libraries, such as the SMT library, but this is many times not enough. Some papers have been criticized for using random data because it's believed that random and real-world objects behave in a different way. So using random data is not an option. And that's why we wanted to study the different ways of generating synthetic data that so that it behaves similarly to real world data. In order to do this, we needed to define what does it mean to behave similarly to real world data. So we created a tool to study how similar two families of problems were, or how, well, if their properties were similar or not. In order to do this, we focused on studying the number of real roots of the univariate polynomials that are generated when the polynomials in these problems are projected. And we used the bootstrap method, that is a standard statistical method, to determine if the number of real roots in two different families followed a similar distribution. So if this feature is similar in both families, we can not conclude, but we have an idea that at least in some way the families are similar. But if this distribution is different in both families, then we know that the families are farther apart. We wanted to compare families from different origins, so families coming from real world and families coming from random or synthetic. But in the process, we observed that the families of real world problems are very different to each other. And as we will see later, this can be an issue when trying to train machine learning model with them. The three origins we will use for our polynomials will be real world polynomials, real world problems, sorry, that will be extracted from the QFNRAY category on the SMT library. In particular, we will use two folders, the multitasking folder and the GeoGebra folder that Matthew and I recently submitted to the SMT library. And we will also talk about synthetic problems that have been created using random poly in Maple, conserving some of the features of the real world problems, such as, for example, using only coefficients or degrees that were used in real world problems, and also conserving features such as the variable structure, we could call it. And there is more detail in the other talk, and hopefully, if there is a paper, there will be more detail in there. And finally, the random problems that were just using rand poly with some values that we decided randomly also. So how do we compare two families? So we will compare the number of roots of the polynomials. So basically what we want to see if two lists of numbers were generated using the same distribution. Our hypothesis is that both lists, that we will call sample 1 and sample 2, were generated by the same distribution 1. And we want to challenge this hypothesis. We want to test if it's true or it's false. So for that, we extract an auxiliary sample from this distribution, and we compare the probability of this auxiliary sample with one of our initial samples. If one of our initial samples is more probable than the sample that was actually extracted from the distribution, then it's likely that sample 2 was also extracted from the distribution, and therefore our hypothesis is true. In any other case, this might indicate that our hypothesis might not be true. This is repeated many times, as I said before, replicating the idea of the bootstrap method that Ferron et al. Proposed in 1995. And this allows us to get a closer idea to how likely is that the hypothesis is true in reality. So the results we got were this. How to understand this table? Well, we're basically comparing how much certainty we can discard that the name family is the same as GeoGebra. So here we are comparing GeoGebra with itself, here random GeoGebra with GeoGebra, here random with GeoGebra, and here multitasking with GeoGebra. The bigger the number is, the more evidence there is that the samples come from different distributions. And it is standard to discard the hypothesis if these numbers are higher than 0.95. So clearly we can discard that Metitarsky and GeoGebra are the same family. And we can see that random GeoGebra that was generated conserving some features of GeoGebra is more similar to GeoGebra than random that was generated without ever knowing about the GeoGebra family. And also we see that Metitarsky is super different from GeoGebra, and this gives us a hint on how heterogeneous the SMT library is. So the main conclusions we reached were that conserving features from the original family results in similarities on the distribution of the number of real roots. We also conclude that there is no such a thing as the properties of real-world polynomials, because as we have seen, the Metitarsky family and the GeoGebra family are very different. And this might indicate that the QFNRAY collection is quite heterogeneous. And this is a problem when training a machine learning model, because also this collection is imbalanced. This means that most of the examples in this collection come from the Metitarsky family. And this means that if we train a machine learning using this collection, maybe it learns how to perform well on examples coming from Metitarsky, but maybe it doesn't learn a lot when it comes to learning about other families. So one must be careful about this. And if there is a paper, there will be a more exhaustive analysis of how heterogeneous the QFNRAY collection is. There will be also analysis of how much the distribution of the number of real roots, basically how much does the family change when different features are conserved. So let's say that instead of conserving all the things I mentioned before, we only conserve the coefficients. Does that make the family similar or less similar? And then we will also put some possible solutions to the imbalance and the heterogeneity of the QFNRAY and other collections, so that future researchers can use this library, this collection properly to train machine learning models. And in the future, personally, I would like to compare the performance of real-world data, the performance of how good the models perform on real-world data, depending on whether they have been trained on real-world data, on synthetic data, or in random data. Well, this is my presentation. I hope I have been clear enough. And if you have questions, I will be very happy to answer them.
All right. Thank you, Tereso. Are there any questions from the audience? You can put them in the Q&A in the chat. I had a question about, I went to the SMPlib benchmark library to look at the QFNRAY collection. I didn't see any collections of benchmarks labeled GeoGebra. Are those compiled from some of the other things in there, or am I just looking at the wrong repository?
Yeah, no, you're completely right. Right now, there is no GeoGebra family in the QFNRAY collection, but Matthew and I submitted it the other day, so hopefully soon it will be there.
Okay, thank you. Otherwise, yeah, this was interesting work. I would like I like the idea of trying to compare real world examples to synthetic ones. And actually, there's a question in the chat or a comment from Rob Corliss, and he says, I have a problem with calling something real world because there are many contexts. For instance, for univariate problems, characteristic polynomials that come from symmetric matrices, which are very common in the real world, those all have real roots, or they have all real roots. So that's, so he
yeah. So
anyway.
in this work, we defined real world problems to the problems that appear in the QFNRAY category. I mean, it's true that we put these things to the side of real world because, of course, like saying that something comes from the real world has many interpretations. This is just our definition that we use to give it a name. We will have called it QFNRAY problems.
Yeah. All right. Okay. Yeah. All right. Thank you very much, Tereso. There will be some time for more questions at the end.
Yeah, it was my pleasure.
We'll move on to our next speaker, who will be Erik Postma, who is a person you may know from MapleSoft. And he will be presenting joint work with Mark Moreno-Maza, and we'll be speaking on substituting units into multivariate power series. And it was not the kind of units you thought. If you is me,
right. Yes,
it's a different kind of units.
Indeed. The reason that John says that is because I also work on the package for units of measurement in Maple, but this is different. So let me get started. The context here is a package called Multivariate Power Series, which we introduced in Maple 2021. And if you don't know anything about it, the only thing you really need to know is that it is lazy. We don't mean that as a character trait. It means just that it is set up to compute a bunch of coefficients of a power series. And then if you want more coefficients, you want to know the result to a higher precision, you can get those additional coefficients relatively cheaply. And it also supports multivariate expressions natively. So let me just give you one example of how it works. Here we have a power series. We specify it by giving a procedure that gives you the dth degree homogeneous component. And now we have this object, and we can say, please truncate it to degree 4, homogeneous degree 4, and we get what this thing looks like, truncated to degree 4. We can do algebraic operations on this thing and get a new power series and truncate that. And now we get the results here. And just to give you a bit of the flavor of sort of what goes on behind the scenes. So if we look at, so the main interesting, important thing in one of these objects is what we call the generator procedure, which is essentially the equivalent of this procedure that you see here, that I entered here, that is used to compute one homogeneous component of the result. And I can show you what that looks like for this object Q, which is the sum of P and minus 1 over P squared. Now, this is not really legible. The reason is that we use some preprocessor macros. If you look at the actual source code, then it's very simple. The object has two what we call ancestors, A and B, which correspond to P and minus 1 over P squared. And in order to get the dth homogeneous component of Q, what you do is you compute the dth homogeneous components of A and B, and you add them together. That's pretty straightforward, right? Okay, I'll skip over this section. And I want to talk now a little bit about substitution. So we wanted to add substitution of one power series into another to the package for this year. This is relatively straightforward if the object you're substituting into the other power series is not invertible. Basically, if that's the case, then it's just a matter of bookkeeping. So there is still a lot of bookkeeping, but it's manageable. So here's what that looks like. We have this P, which we looked at before, and we now substitute Q for X in P, and now we can again request the truncation to degree 4. Wonderful. I'm again going to skip over the rest and talk a little about substituting units into paraseries. So a thing is a unit if you can invert it, and that means that the constant component is non-zero. And you can see fairly easily that this is not going to be very simple by taking sort of the simplest non-trivial example that you might come up with, which is take the power series for e to the x. And we want to substitute that into itself. So we would expect that to evaluate to the power series for e to the power e to the x. And if you look at that, you see something fishy. Now, if this were an interactive thing where you could immediately give me answers, I would ask you, what is fishy about this? Well, the answer is there is this non-analytic number e in here, and there's no way that you're going to get that by doing some finite number of operations on a finite number of, or rather a finite number of analytic operations on a finite number of analytic of rational numbers, which you would get as the inputs from your two input polynomials or input power series A and B. Sort of traditionally in the literature, doing this operation, substituting a unit into a power series, is considered not well defined, and we move on to doing something else. However, I thought about this for a bit, and I thought, wouldn't it be nice if we could do it anyway? And I implemented it. So here we see that the outcome we get here is exactly what we expected. So clearly something is happening to make this work. And the trick is, of course, that I cheat. Always the best strategy if you want to do something that is impossible, is to cheat. Which is I use something that frequently the multivariate power series package has access to, which is an analytic expression for the value that the power series converges to. So there's an ugly formula here, but it says something very simple. What you can do is you can just substitute in the simplest case the analytic expression for the one power series into the analytic expression for the other power series, and just generate a new power series for that thing. There are some tricks to make this work a little bit better, which I will once again, for reasons of time, not go into. I just want to say a few words about the history of this idea. So I was thinking about doing this at the start of this year, and working on the non-unit case and sort of writing out the bookkeeping equations. And I looked at that and I thought, I think if I sort of squint at this carefully, or squint at the formulas, I think if you do it carefully, you might be able to use this analytic expression to have some of those sums that wouldn't converge for the unit case, make them converge. And I sat down and I wrote a very long, basically I threw algebra at the problem, and I started here with sort of, let's take a bivariate example and substitute some things into it, and I got a long derivation that obviously I will not go into, that ended up with an ugly, complicated formula that nonetheless you could get a result out of. I implemented that and it worked, and I wanted to show this off at this conference. But when I was about 90% done writing the paper, I realized that by using the analytic expression, I could just do it simpler and substitute the two analytic expressions into each other. And this long derivation and the very complicated implementation weren't needed. And I got a much faster and simpler implementation out of it. So that's sort of a little bit about the story of how I got to this result, and that brings us to the end of my presentation here. I'd be happy to answer any questions.
All right, thank you, Erik. So I can't tell if Rob Corliss is trolling you in the chat or whether he has some serious questions. He actually asks if you can demonstrate Newton's method for multivariate power series division live so that everyone can see how easy it is. But I think that was, I think he's trolling you there. But you can go.
I'm not going to do that.
But
think about that, especially because I don't think I've implemented derivatives yet for these things, which of course would be relatively easy to do, and it's on our list, but it's not in there yet. So
he has another question. He asks about, does the idea of reversion work in multivariate power series, so that if you have something like z is equal to f of xy, to solve for y as a multivariate power series in x and z?
Yes, you can do that. I think there are conditions. I think there are conditions on that, but there are certainly cases where it can work. You can similarly, you can what many people do, of course, is basically use this sort of technology to solve differential equations in a series sense. But yes, inverting, sort of functional inversion should also be possible. Yeah.
Okay, thank you. Looks like he has one other question but I'm going to leave it to you to type an answer if you like. But I will also open up the floor to, if anyone has any questions for any of the presenters. We have just 1 or 2 minutes left. But happy to. All right. Well,
I have a comment here, if I may, and maybe that's exactly what you're doing, Erik. But I mean, you can always subtract the constant coefficient.
Yes, that's one of the tricks. So really, what you need is only an analytic expression for the power series that you're substituting into.
Yeah, exactly.
Yeah, I think Erik covers that in the full talk.
That's right. Yeah,
which everyone should go watch. It's in the theater archive. All right. Thank you very much to everyone in this session, Amir, Hosein, Tereso, and Erik. This concludes the first session of the algorithms and software session. We'll have a 15-minute break, and we'll be back at, I guess, 11:20 Eastern time. Anyway, thank you very much, and hope to see you all in the art gallery reception, which will be at noon. Anyway, bye everyone.